Hey everyone, and welcome to This Explainer. I'm so glad you're here. A lot of people look at algebra and just see this intimidating wall of scary letters and numbers. But I promise you, by the end of our time together today, you're going to see that polynomial formulas are really just predictable, totally logical patterns that are just waiting to be discovered. And they are absolutely everywhere. Every time a store calculates a complex shopping discount, or an architect designs one of those beautiful curved building roofs, or even when a surveyor measures a plot of land, or your phone compresses data so a video streams smoothly, polynomials are working hard behind the scenes. Today, we're going to unlock exactly how they work. So take a deep breath. We're going to take this step by step, almost like a private tutor session. All right, let's dive right in. Okay, before I throw any formulas at you, I just want you to look at a pattern. Look closely at the numbers in this specific polynomial right here. 2x squared minus 8x plus 6. We've got a 2, a negative 8, and a 6. Now, there is an actual magical secret hiding in plain sight between these specific numbers and our final answers, which we call the zeros of this equation. See, I don't want to just give you a rule to memorize today. I really want you to see the logic for yourself. So let's crack this open. Let's see how this builds using a skill you might already know, which is splitting the middle term. To find our zeros, we just take that middle term, the negative 8x, and we split it into negative 6x and negative 2x. Notice how if we group them up and pull out the common factors, we get our final factored form, which is 2 times x minus 1 times x minus 3. So for this whole thing to equal 0, x has to be either 1 or 3. You can see those final zeros right there, the 1 and the 3. Now, do me a favor and hold those numbers in your mind, 1 and 3. Because here comes the magic. Now, what's really interesting is the perfect match we're about to uncover. Let's take those zeros we just found, the 1 and the 3, and let's just add them together. The sum of our zeros is 1 plus 3, which equals 4. Simple enough, right? But now, look back at our original numbers, the 2, negative 8, and 6. What happens if we take the negative of our middle number, the coefficient of x, which is negative 8, and divide it by our first number, the coefficient of x squared, which is 2? Well, negative 8 becomes a positive 8, and 8 divided by 2 is 4. No way, right? They are exactly the same. You might be thinking that was just a lucky coincidence. Well, let's try multiplying them and see what happens. The product of our zeros is 1 times 3, which obviously gives us 3. Now look back at our original numbers one more time. Take the very last number, the constant term, which is 6. Now divide it by that first number again, the 2. So 6 divided by 2 is exactly 3. It's a perfect match, again. This means that without having to do all that long, complicated factoring we just did, the original equation literally tells us what the sum and the product of the answers are going to be right from the start. To turn this neat little trick into a universal rule, mathematicians like to use a couple of friendly Greek letters, alpha and beta. Now, I know Greek letters can sometimes look super intimidating when you see them on an exam paper, but please do not let them scare you. They are literally just placeholders. It's so we don't have to write out the words, the first 0 and the second 0 over and over again. We just write alpha and beta. It's just shorthand, that's all. Let's actually look at why this works, because understanding the why is absolutely crucial for beating math anxiety. Any quadratic polynomial, which we usually just write out as ax squared plus bx plus c, is really just its two zeros, alpha and beta multiplied together. It looks like x minus alpha times x minus beta, along with some constant multiplier on the outside that we'll just call k. When you expand those brackets by multiplying everything out, you naturally get a middle term that contains the sum of alpha and beta and an end term that contains their product. It's not just some random rule you have to memorize. It's literally the structural DNA of the math itself. So the bottom line is summarized beautifully right here. If you have any quadratic polynomial, the sum of its zeros, alpha plus beta, is always going to be negative b over a. Always. And the product of its zeros, alpha times beta, will always be c over a. We've just built an incredibly powerful tool. Now let's become masters at actually using it by solving 3 examples together. These are exactly the kinds of questions you'll see on tests, and we'll start easy and work our way all the way up to board exam level. Ready? All right, here's example 1. I like to call this one the easy one. The question asks us to find the zeros of the polynomial x squared plus 7x plus 10, and then verify the relationship between those zeros and the coefficients. So they give us the equation, and they want us to find the answers and basically prove that our shiny new rule actually works. Let's walk through this step by step together. First up, we need to factor x squared plus 7x plus 10. We need 2 numbers that multiply to 10 and add up to 7. That's pretty clearly 2 and 5. So it factors nicely to x plus 2 times x plus 5.
Now, pause right here, because this is where a ton of students make a classic mistake. They see the 2 and the 5, and they think, great, those are my zeros. No. Remember, we need the value that makes the whole bracket equal 0. So our zeros are actually -2 and -5. Let's verify our rule. The sum of -2 and -5 is -7. According to our new formula, -b over a would be -7 over 1, which is -7. It's a match. And for the product, -2 times -5 is +10. Our formula for c over a is 10 over 1, which is 10. Boom, works perfectly.
Okay, moving right along to example 2. This is our medium challenge. The question says, find the zeros of the polynomial x squared minus 3 and verify the relationship. Now, looking at this, you might have a tiny moment of panic, like, wait, where's the x term in the middle? Don't worry, take a breath. If a term is missing, it just means its coefficient is a 0. The math hasn't changed, the pattern is still completely intact. To instantly crack this problem wide open, let's recall a classic algebraic identity. A squared minus b squared equals a minus b times a plus b. We can apply this right to our problem. We can think of 3 as the square root of 3 squared. Make sense? So x squared minus 3 just becomes x minus root 3 times x plus root 3. And just like that, we've totally unlocked the zeros. They are simply positive square root of 3 and negative square root of 3.
Let's walk through the verification, just to prove our missing middle term doesn't break our new rule. The sum of positive root 3 and negative root 3 is obviously 0. Using our formula, -b over a is -0 over 1, which is 0. Perfect. Now the product. Root 3 times negative root 3 gives us -3. And using our formula, c over a is -3 over 1, which is -3. It's entirely consistent. See? The numbers always tell the truth.
All right, time to level up example 3. This is a classic board exam level question, and notice how it flips the script entirely. The question asks, find the quadratic polynomial whose zeros are 2 and -1/3. Notice what's happening. This time, we aren't given the equation. We actually have to build it from scratch using the answers. We are essentially working entirely backwards.
So first things first, let's identify exactly what we have. Alpha is 2, and beta is -1/3. Step 1 is always to find our sum and our product. The sum, alpha plus beta, is 2 plus -1/3. Now get a common denominator, that's 6/3 minus 1/3, which gives us a nice sum of 5/3. Take your time here. Seriously, fraction addition is where so many silly, avoidable exam mistakes happen. Next up, the product, alpha times beta. 2 times -1/3 is simply -2/3. So we've got our key pieces, 5/3 and -2/3. Let's see how this builds into an actual equation. We substitute our sum and product right into our general template. Remember that constant multiplier we talked about earlier? We write k, open and bracket, then x squared, minus the sum times x, plus the product. When we plug our values in, we get k times the quantity x squared minus 5/3 x minus 2/3. Now, honestly, that looks a bit messy with those fractions, right? Exam graders generally want to see a nice, clean polynomial without fractions everywhere. And this right here brilliantly illustrates the power of that letter k. That k is a constant multiplier, meaning it can be any non-zero real number we want. So we can just pick a smart value for k to perfectly cancel out those annoying fraction denominators. Since our denominators are both 3, let's just choose k equals 3. When we multiply the whole thing by 3, the fractions just vanish. 3 times x squared is 3x squared, 3 times -5/3 x is -5x, 3 times -2/3 is -2. So our final, beautiful, perfectly clean answer is 3x squared minus 5x minus 2. You guys have done fantastic work following along today. Let's wrap this all up. Here is your Ultimates 5-point cheat sheet. Honestly, take a mental screenshot of this right now. The general form is ax squared plus bx plus c. The sum of the zeros is always -b divided by a. The product of the zeros is always c divided by a. If you lock this structure in your head, literally no polynomial exam question will ever be able to intimidate you again. And hey, I promised you a surprise trick to solve things faster in your exams. When a question gives you the zeros and asks for the polynomial, do not try doing some complex reverse factoring. Just use the k trick we just learned. Find the sum, find the product, plug them straight into the k template, and then just choose a value for k that instantly wipes out any fractions. It saves you so much time, it totally prevents errors, and it gives you a perfect, clean polynomial every single time.
Honestly, consider it your new secret weapon.
So there you have it. You've seen the shape of these equations, you completely understand the logic behind them now, and you just conquered the hard board-level exam questions. Mathematics really isn't about memorizing a bunch of scary formulas. It's about uncovering the beautiful, logical stories that numbers tell us every day. And you have the tools now to read those stories. Keep exploring, stay focused, and ask yourself, what mathematical pattern will you conquer next? Thanks so much for joining me on this explainer. You've got this.